The definite integral is then the area under the curve. And this definite integral, in this case, the area from A to B, can be found by the displacement on the antiderivative. And again, this is part 2 of the fundamental theorem of calculus. So if I want to calculate that exact area, I can take the antiderivative function, big F, and find the displacement or the difference between big F at B and big F at A. So looking at this curve here, I want to find the area under the curve of sine x from 0 to pi. Now the area under the curve from 0 to pi, this area in here, is an awkward shape. Okay, there's no geometric shape that we can formula that we could use for that. But since we know that the area underneath this curve can be represented by the displacement on the antiderivative of sine x, what I can then do is say that the area is equal to, well, the antiderivative of sine is negative cosine of x. And I can evaluate it from my bounds. So this vertical line represents a line to keep track of my bounds. And that's going to be what the difference between negative cosine at pi minus negative cosine or plus cosine at 0. Well, cosine at pi is negative 1, so I get negative of negative 1 is 1, plus the cosine of 0 is 1. So that area works out to be exactly 2 units square. Okay, and this is interesting because if you take a look at that shape, well, that shape has a height of 1, a width of approximately 3.14, and that area inside that, if we kind of imagine the rectangle here, the area inside that rectangle, this area, the yellow area, is going to be exactly 2. Okay, and that kind of makes sense because the rectangle is going to be about 3.14, and that's about 2/3 of that area. And it's interesting because it is exactly 2. So this strange shape is giving us exactly 2 square units. Looking at this next one here, we're going to do the same thing. We can't, to find the area of this shape, whatever the shape looks like, it's going to be an awkward shape, but we can use the fundamental theorem of calculus to say that, well, if we can anti-differentiate this, we can use that antiderivative to work out the area. So I'm going to say the area is equal to that shape. Now, to do this, we need to use a substitution. The inside function, its derivative, is accounted for by the outside. Okay, so I'm going to let u equal x squared. My du is then going to be 2x times dx. Okay, so that 2x times dx represents the outside part of this. Now, we have to be careful here because once we change our variable from x to u, we do have to make sure that we represent that in the bounds. So x equals 0 and x equals pi, because our expression now is going to be in terms of not x, but it's going to have a u in it and a du. Okay, so whenever we do that, we need to make sure that we indicate that in our bounds, and our bounds are in terms of x and not u. Now we could also convert the x into a u using this expression. So we can say it's u equals 0 to u equals pi squared, but it's probably easier just to leave it like that. But once we've done that in terms of u, we're going to anti-differentiate this. So again, we get negative cosine. In this case, it's going to be u. Our bounds are going to be in terms of x, from x equals 0 to x equals pi. I'm going to change this back into x's. So cosine of x squared. And now my bounds, I don't need to indicate that they're in terms of x because my variable is in terms of x. Okay, so when I work this out, I'm going to end up with negative cosine of pi squared minus negative or plus cosine of 0 squared. So this works out to be 1 minus cosine of pi squared. And that's going to be units squared because we're representing that as area under a curve.